Happy Monday, everybody, and welcome to another episode of Echo Live, coming to you from the Michigan Science Center. My name is Anna, and it's so great to have you guys here today to talk about another really awesome science topic. Today, we'll be talking about high voltage electricity. So if you haven't done so already, use the chat feature either on Facebook or on Zoom to introduce yourself. Tell us who you are, maybe where you're watching from, or even what grade you're in. We see lots of familiar faces, so hello to everyone who's been joining us for our Echo Live programs every day. I see some of our friends from Kansas have signed back on. I see some familiar faces on Zoom as well, so thank you guys so much for continuing to join us every weekday at 2:30 p.m. Eastern for Echo Live. So today we're going to be talking about electricity, but not static electricity like we discussed during our first electricity program. Today we're talking about something called high voltage electricity. So to first understand what makes this electricity a little different, the electricity that we'll be using today, we need to talk about safety. So we all know that electricity in any form can be dangerous. And so even on today's program, I am not playing with electricity. I'm sure you all know that you should never play with electricity at home or anywhere else. We've talked about this a little bit already because electricity can be very harmful to people. But we're going to be very safe here inside the studio today. So I'm taking lots of safety precautions. And again, I am never playing with electricity. We are only ever safely experimenting with the electricity and the electrical equipment that I've brought to show you guys today. So to understand what voltage is, right? When we talk about electricity, we often talk about two terms. We talk about voltage and current. Now, if we're not super familiar with electricity, which is okay if you're not, because I didn't learn a lot about electricity until I got to college. But if we want to understand what makes electricity dangerous, we have to break down those two terms. Now, you can tell me in the comment section, or maybe we can do a poll using our reactions. So we want to talk about which one, when we're talking about electricity, which is more dangerous to people? Is it voltage or is it current? So you can tell me in the chat, is it voltage or current that is more dangerous? If you'd like to use the emoji features on Facebook, you can either give me a thumbs up if you think voltage is more dangerous, or you could give me a heart if you think current is more dangerous. So go ahead, tell me what you think. Which of those two terms, so right now we're guessing. So if you don't know, it's okay to take a guess, and we're going to talk about the answer together. So tell me, which is more dangerous? Is it voltage or current? I'm seeing a couple friends in the chat are already making observations about electricity. So they're telling us that lightning is a form of electricity, and you are absolutely right. We talked a little bit about lightning in our last electricity program, and we'll talk about it a little bit more today. I'm seeing a couple thumbs up. I'm seeing a lot of friends in the chat are telling me voltage. I see some votes for voltage. I've got a couple votes for current from Elnora and Adam and Cindy. So we're not sure. Or maybe we are looking for some more information, but I see some great guesses coming in, probably based off your prior knowledge. Now, maybe my first slide could have contributed to your guess. So I did say danger, high voltage. And of course, any aspect of electricity can be dangerous. But when we're talking in terms of what could be very harmful to humans, especially, we're really talking about current. So voltage is strictly the amount of electricity that is flowing through a circuit. It's the difference in electrical charge between 2 points. So if you have a big difference between two electrodes, you have a high voltage. But we say current is the more dangerous part of electricity because current is the speed at which that voltage travels through a circuit or through a person. To demonstrate this, I brought with me this little contraption that I've rigged up. So I didn't have a Slinky here at home. A Slinky works really, really well for this demonstration, but all I've done is I've coiled up some wire so it's still kind of elastic, kind of springy, like a Slinky is. And I've strung some beads onto it. And so you can see that there are beads. Let me go ahead and zoom in just a little bit. We'll get off that demonstration. And we'll look just up at this Slinky that I have in my hand. So here I've strung some beads onto our circuit. So we're going to refer to this spring or this Slinky as our circuit. The beads are going to represent the amount of voltage, the actual amount of electricity that we're going to put through our circuit. So you can see that we've got a large amount of beads over on one side of the circuit and not a lot of beads over on the other. So there's a pretty big difference in current between these 2 points. So voltage is just the amount of beads. We can think of it that way in this experiment. But when the beads aren't moving, right, they're not super harmful to us. We could have 1 bead, we could have 1,000 beads, but if they're not moving, they don't cause much of a danger to people, right? So if we want electricity to flow, we need the electrons to move. We need these beads to flow through our circuit. So we can refer to current as the movement of these beads. So the way we'll get these beads to move is actually by pulling the spring apart, so pulling down on it, and we can see that then we get the beads to start moving. The faster these beads move, the higher current we say we've created. So voltage is the number of beads, but current is that speed that the beads move at. So the harder I pulled on the spring, right, the faster those beads would have moved. So the faster the electricity travels through or with more force is actually what's very, very dangerous. So if your beads were moving very slowly, kind of like they are right now, not super dangerous, right? Because that would represent a low current or a low amperage. When they move really quickly, that's what we say is dangerous in terms of electricity. Now, one thing that can affect current can affect the speed at which current travels through a circuit is the type of medium that you let it travel through. Generally, we say that things are either conductors or insulators. Not conductors like the person who drives a train, but something that allows electricity to flow through it very, very easily. Don't worry, Louie, I see he made a comment that I wrecked a slinky. I actually didn't have a slinky, so that was just some aluminum wire. I have tons and tons and tons of it. And if you did this, if you recreated this at home with a slinky, it would regain its shape right away. So my wire didn't do a great job of recoiling, but I didn't ruin it. Don't worry, I can use that wire again later and you'll see why. So when we're talking about conductors, right, we say things are either good conductors, meaning they really easily let electrons or electricity flow through it very, very easily or very, very quickly. But if you use something that's more of an insulator or a less good conductor, right, you can actually slow down that current, therefore making it a little less dangerous. So go ahead and tell me in the chat, what is an example of an insulator? Something that does not allow electricity to flow through it. Tell me, what is an example of an insulator? So again, not something that is good for carrying electricity, something that's not so good or even bad at carrying electricity. Go ahead and tell me, what is an insulator that you know of? You can think about the things on my table, think about the things that you have in your home. What types of materials? Suzanne told me that rubber is a great insulator. And that's exactly right. Rubber is a great insulator. It really does not allow for really any movement of electrons through it. And so rubber is a great insulator. I see that someone told me wood is another great insulator. So I do have a piece of wood up here on the table. My table's even made of wood. So wood doesn't really let electricity travel through it very, very well. Some of my friends in Zoom told me wood, certain kinds of toys, right? So I'll think about what toys are made out of. Maybe certain toys can carry electricity, right? If we think about our electronics, those are designed to carry electricity in them. So those things are mainly made of metals and things like that, but other toys may be things that are made of plastics, right? Plastic is another good insulator. Doesn't really allow for that flow of electrons or that movement of electricity. Oh, I see you guys for water. Water is a great conductor. So we don't want to ever put water near any sort of electrical device. That's actually why people are such great conductors, right? Because we are mostly made out of water. There's water inside all of our cells, flowing through all of our human body systems. It's what keeps us alive, but it's also what makes us such good conductors, which is why people need to be really careful around electricity as well. All right, so we've seen some really great guesses, and a couple of our friends on Zoom and in Facebook told me that wood is not a great conductor. So we're going to do an experiment with this piece of wood. using this electrical device that I have on my table. Now, this electrical device is actually what's going to provide all the high voltage electricity that we're going to use today. So this is what we call a transformer. A transformer is an electrical device that can actually increase the amount of electricity that it carries from where it gets it from. So this transformer is plugged into an outlet in the wall. If you're familiar with the outlets at home, we know that each one is about 120 volts. Really, it gives out about 110 volts by the time it gets to the device that it's powering. But every outlet gives out about 110 volts of electricity. What's special about these transformers is that inside them, there's thousands of tiny little coils, just like the coil I showed you earlier, and they're wrapped around really, really tightly, and that can actually increase the amount of voltage that it outputs. So even though only 110 volts are flowing inside it, after the electricity leaves all those thousands and thousands of coils, it's actually about 6,000 volts by the time it leaves, which is an incredibly high voltage, right? So this is a very dangerous piece of electrical equipment. You can't just find them anywhere. You have to be highly trained and know how to use it safely. So I do have some rubber gloves. So you friends at home already told me that rubber is a great insulator. Even though we're going to be very careful not to ever touch the electrodes, which are these two red and black ends of the cords that are attached to this transformer. One is negative, one is positive, and that's going to allow for that movement of electrons between them. So even though I'm going to be very, very careful never to touch them while they're on, I am going to wear these gloves just for that extra layer of protection. So since these are made of rubber, if something were to come in contact with them, they'll stop that flow of electrons. Therefore, they're protecting me from the electricity. So again, we're always being safe, and we should never, ever play with electricity at home, okay? All right, so let's go ahead and I'll zoom over on my piece of wood. And you'll notice that I've put two metal screws. So if we think about good conductors, right? Metal is a good conductor. So that's actually how we're going to attach our electrodes to the wood. So we'll go ahead and we'll add one electrode to each side. So we've got one electrode over here, one electrode over here. And once we turn on our transformer, there will be a 6,000 volt difference between these 2 points. And let's see what happens when we send that electricity through the wood. So here we go. We're turning on our transformer, making sure to keep our hands away from our electrodes over there while the transformer is on. Now this transformer does not make a noise, so you won't know that it's on other than the fact that I'll tell you when to turn it on and when I turn it off. So here we go, turning it on in 3, 2, 1. Now, we can leave it on for a couple moments here to make sure that we're really sure that really nothing is going on, right? You already told me that wood is not a great conductor. It doesn't really allow for that movement of electrons between it, especially because this wood is dead, right? This tree has been chopped down, even though plants, just like people, are usually full of water. Since this wood is dry and dead, there's no longer the ability for electricity to pass between those two electrodes. So we'll go ahead and we'll turn our transformer off. So now our transformer is totally off. There's no electricity flowing through these electrodes. We'll go ahead and set them back over to the side. But what we can do is, instead of using that piece of wood, I've already set up a different piece of wood before this program, but this one's going to be a little bit different. So this one, I've actually had a wet rag kind of soaking the surface of the wood. So we talked about that wood wasn't a great conductor, especially because it is dry, but instead we're going to replace it with this damp piece of wood. So you can see that the color's a little bit different because it's soaked with water. You might also notice that there's something on the surface. So I've also sprinkled some salt across the surface. Salt water is a much better conductor than fresh water because of those ions inside. So those ions, like salt, actually help it to carry electricity through the water. So we'll tuck our electrodes down here. So we're going to find out here, right, why we're always so careful to keep water away from electrical devices. So we'll turn on our electrodes here. And you already noticed something happening near the black electrode, right? You might be able to see some sparks, but we're going to let this circuit keep building here. We're going to keep our electrodes on, powered on. Now, people actually use this exact process, this hooking up electrodes to damp wood, in order to create some pretty beautiful art. So by dampening the wood, I'm seeing a lot of effects on the side. I'm hoping it's starting to travel to the front. There it goes. But we're actually letting the electricity flow through the wood, or really through the water. And since this electricity is coming in contact with the air around it, right, we're starting to have some combustion, or a combustion reaction taking place. And it's really spreading over on the side. We can see it near that black electrode. We'll see if it runs out of water on the side and chooses a path across the front. Now this process takes a little bit. I actually have a fan going in here because there is a small amount of smoke that's being generated, but I have fans set up to kind of pull that smoke outside. And we can see that although this wood wasn't a great conductor while it was dry, right now that we've made it wet, we're actually able to see more of that movement of the electrons. So Jamie asked a great question. She asked, what would happen if the tree were alive? We know that lightning often strikes trees, right? Mainly because they are tall and they make for a good path between the lightning in the sky and the ground. But trees can conduct electricity, especially when they're living and full of water and ions. Let's keep an eye on the chat and see if we have any questions while we let this go. The wood is also getting hot, not so hot that I couldn't touch it, thankfully. So I will be able to, once I take the electrodes off, I will be able to touch the wood. Wood, like we said, is a good insulator, meaning that it doesn't allow for a lot of movement of electrons, but it also doesn't allow for a change in temperature very quickly either. Does lightning move fast in a pool? Yeah, absolutely, right? So we know that any source of water you're told to avoid when you are in a lightning storm, right? Because water is a great conductor. There it goes. Now our electricity is starting to spread across the front of our wood here, right? Now it takes it a while, right? Because this electricity is fighting to form a path over to the other electrode. So it's flowing from the black electrode to the red one, and it is fighting for that path across. It's pushing through the wood, it's reacting with those ions, that salt on the surface, and it gives us that really, really cool effect. So we'll go ahead and we'll shut off our transformer for now. I did bring one that I created earlier. So our transformer is off. As I said, we can tell there's no movement of electrons, that electricity has stopped flowing. We'll disassemble our electrodes here. And I'll show you the one that I made earlier. So it does take a small bit of time, right? But we can see that eventually that electricity wants to find a path. It wants to form a complete circuit. And so it started from the two ends. There was two screws in this piece of wood, just like I have in the one we just looked at. And the electricity fought its way across the ions on the surface until they finally met in the very center. So where they finally meet, it completes a circuit. The electricity is happy, and it can stop kind of burning the wood around it. Yeah, so if you noticed, we had a lot of movement up the back and the side, probably because we got a lot of soaked water right here on the corner. So we had a lot of that moisture and that water for it to travel through. The back is almost completely untouched because I didn't dampen that side of the wood. So the electricity really traveled through the wet side of the circuit and created this really cool kind of interesting artwork. So of course, electricity is not a toy. The artists who do use this also wear or also take a lot of safety precautions to make sure that they are safe when they're working with this electricity. All right, now you might notice that I also have on my table another piece of familiar equipment that we've used on Echo Live, and we're going to kind of combine these two pieces of equipment. So we're going to combine our vacuum and vacuum chamber with this high voltage electricity. So someone did ask on a different Echo Live program, what happens to electricity in a vacuum? Electricity can still flow through a vacuum. Electricity doesn't need oxygen or air in order to travel through. All it needs is a conductive medium. So at the top, we have two metal bars, which are going to be attached to our electrodes. And then down inside the jar, I've hung up more of that aluminum wire. So this is another kind of art project that I've created. And we're going to find out what happens when we push this electricity through a vacuum. So a vacuum that meaning we're taking away all the air from inside this chamber. but the electricity is still going to flow through those two electrodes. So we'll go ahead. I'm going to zoom in on our vacuum chamber here. You can see that I've arranged the wire inside to look kind of like a lightning bolt. I will be stepping out of the way, so I'm going to turn off our virtual background here, just to make sure that it's not distracting, that we're able to see that little lightning bolt that I've hung inside the vacuum chamber. So again, I'll put on my rubber gloves so that we can attach our two electrodes to the top of the jar. So we've got, make sure we put these in the back. We've got our black electrode hooked up. We have our red electrode hooked to the top. And so we'll have a difference, right? A potential difference between those two wires that are hung inside. You'll notice that at the bottom, right, there is a small gap between them. That's just so that we don't short out our transformer. So we don't want too much of a flow of electricity, even though it won't break the transformer. But we just want to make sure that we get the effect we're looking for. So I've created a small break inside. So we're first going to remove the air by turning on the vacuum. That will remove most, but not completely all of the air from inside the chamber. And then we'll turn on the transformer. So here we go with the vacuum. All right. So the air has been removed. The air has been removed. To see this better, I'm actually going to turn off our lights. So next goes our lights. And here we go with our transformer. So the transformer is going on in 3, 2, 1. Now, if you know what this is, if you know what we've created inside the vacuum, go ahead and tell me in the chat. Think about our states of matter. Think about what we talked about with our last static electricity demonstration. Tell me what we've created, or what does it look like to you? A couple friends in the chat on Zoom have told me it looks like a light bulb. What else? Go ahead. We'll give you guys a moment to think about this one. Tell me, what does this look like to you? Ooh, someone asked a good question. They asked, why is it purple? We'll talk about that. And someone told me that it looks like a lightning bolt. So if you are familiar with your states of matter, tell me, what state of matter is lightning? Is it a solid? Is it a liquid? Is it a gas? Or is it something else? It does look kind of like a glow stick. So we've basically created lightning here inside the jar. Lightning is a form of plasma. And you only get plasma when you are exciting a gas to the point of ionizing. And we've actually done that inside the vacuum chamber. So something that was important to note. So I'll go ahead and we'll turn off our transformer. The vacuum goes next. And then we'll turn our studio lights back on. Here we go. We've actually created plasma there inside the vacuum chamber. Now, we said that we removed most, but not necessarily all of the air molecules that were inside the vacuum. This vacuum chamber is not perfect. As the vacuum pulls the air out, it does allow for a very, very small, only trace amount of electricity to still be coming through the top of the chamber where we have our electrodes attached. So what happened is, that very, very small amount of electricity, or that very, very small amount of gases actually got ionized by the high voltage current that was moving through the circuit. So all of those ions that came into contact with the wire were actually excited to the point where they turned into plasma. So the gas that we were seeing was actually mostly nitrogen gas. So we said that nitrogen makes up most of the air that we breathe. So that is most of the trace air that was left inside the vacuum chamber. And so we actually created our very own plasma ball. If you've ever seen one of those plasma balls that you could have as a decoration in your house, That uses the same process. That globe is a vacuum, and then you put electricity through the coil in the center, which ionizes those gases or the trace gases inside and turns them into plasma. So different gases will actually ionize and turn different colors. So if you've seen neon lights before, they actually fill the tubes on neon lights with different types of trace gases, which allow them to kind of ionize and turn different colors. Now, you might have noticed that while we had that turned on, I did bring one last piece of equipment with me. But before we get to this very last piece of equipment, I would love to pause and answer any last questions that you might have before we get to our grand finale here today. So go ahead, type your questions in the chat for me. I'll wait for some questions to roll in on both Zoom and through Facebook. Of course, this is the time where we always want to thank our generous sponsors. So our sponsors like the DTE Energy Foundation allow us to bring these programs to you every day at 2:30 p.m. Eastern. Thank you to everyone who has been donating to the Michigan Science Center on their own. So you can make a donation to us either on our website or through the link that we've posted on our Facebook page. We appreciate everyone who's doing their part to help bring these Echo Live programs to Facebook and through Zoom every single weekday. If you're enjoying these programs, as always, make sure that you share them on your Facebook so that others get to enjoy them as well. If you'd like to be notified when Echo Live starts every day, make sure that you are not just liking the Michigan Science Center, but that you are following us on Facebook as well. All right, so let's see if we have any questions in the comments here. So a couple people on Zoom asked me questions. Someone asked, can you control the power of lightning? That's kind of what this device was intended to do. So we'll talk a little bit about how lightning can be used to power cities or how we can harness that power. But we don't normally try to control the power of lightning, right? It's unpredictable. We're not always sure when weather is going to come in. We can't always direct lightning bolts in a very safe way. And so for the most part, we don't rely on lightning for power. Let's see on Facebook. A couple of people asked, can electricity jump? The answer is yes. So even using my transformer that I've used here, they have to get generally close together in order for them to arc or for the electricity to kind of bounce between the two electrodes, but they don't actually have to touch. Electricity can travel through the air as well. So depending on the force of your electricity or the amount of electricity, that allows it to travel through the air as well. So electricity really can jump. So you always want to make sure that you stay far, far, far away from electrical equipment, especially stuff that is very, very high powered or has a lot of current running through it. Is there plasma in outer space? Great question. Plasma is actually the most abundant state of matter in the entire universe. That's because the sun is mainly made up of plasma. So where here on Earth, inside our atmosphere, we get a lot of solids, liquids, and gases. Out in space, right, or on stars are mostly made out of plasma. So we say that plasma makes up over 90% of our known universe because it makes up all the stars, which are much more massive than our planets by far. And so there's no plasma in the vacuum of space, so between those space objects, but there is plasma that makes up all our stars. Does the wire inside the vacuum get hot? Yeah, it does. So because there is some ionization of those gases, it does get kind of warm, not so warm that it would probably burn me. But again, we're always going to be safe, so I'm not going to touch the wire. Since we were removing most of the oxygen from inside there, we didn't have a whole lot of combustion. We didn't generate a great deal of heat, at least in this small version of this plasma reactor. And so it's not extremely hot, but it can get quite warm, especially the longer we leave it on. Let's see. I see a couple of great comments about how we are conductors. That's absolutely right. We are great conductors as well. How can lightning turn off power? And that has a lot to do with resistance of circuits, right? So lightning is extremely powerful, and it has a lot of that potential difference or voltage. And so when it comes into a circuit or something that is meant to hold power, right? If that power is too great, it can damage those equipment, right? Because certain thicknesses of wires and certain materials, certain types of metals can only handle so much flow of electricity over a period of time or over a certain distance. And so if lightning strikes an object and it's too powerful for that object to handle, it can incinerate the wires. They could melt if they get too hot. They could explode in certain circumstances. And so lightning is not so predictable, so we definitely don't want to use it to power up our homes in our cities. So I'm going to go ahead and we'll detach our transformer here. I'm actually going to unplug it so I can scoot it out of the way of our finale, because our finale is going to be this mini Tesla coil here. So we've done one experiment with the Tesla coil already, but that Tesla coil was handheld. This one is a bit larger. Not so large as the one at the Michigan Science Center. So the one at the Michigan Science Center in our DTE Energy Sparks Theater is over 6 feet tall, and it shoots lightning bolts across the entire room. But this thing is very, very cool as well. So this is actually going to shoot smaller lightning bolts, but it's still going to be pretty exciting. Since it is going to shoot lightning bolts, I am going to clear a couple pieces of equipment out of the way, just things we don't accidentally want to get damaged by our Tesla coil here. For this, we'll of course want to turn off the lights since we're going to be creating electricity or lightning strikes coming out the top of our Tesla coil here. So let's go ahead and get a good angle. There we go. All right, so we've got a pretty good angle now on our Tesla coil. I'm going to turn off the lights and then I'll give us a countdown. And what you're looking for is to look at the top of the Tesla coil here. You can look at all different parts of the Tesla coil. The way it works, right, is we just plug this into another of those 120 volt outlets. It's then sent, that electricity is then sent through the copper coils. So this part of our Tesla coil is covered in copper coils, tiny, tiny, very thin copper coils, which is then transforming that power, right? Just like our 6,000 volt transformer that we used for our other demonstrations, we're increasing the amount of power, and then we're shooting it out the top through what we call a spark gap. So as it exits that spark gap, it's under a lot of pressure, and you can think of it like using a hose in the summertime. And so if you were to turn on your hose outside and then put your thumb over the top, that electricity is then the water is pressurized, right? And when you put your thumb over the top, it kind of sprays all over the place. The same thing is going to happen with our Tesla coil here. It's going to shoot lightning bolts because it has so much pressurized electricity inside it. So we'll go ahead. I'm going to turn off our lights. We'll start our countdown, and then we'll go with our Tesla coil. So here we go. The lights are off. And we're going ahead with our Tesla coil in 3, 2, 1. Very, very cool. Now you can probably tell why, even though Tesla invented these in order to power up our homes and cities, why we don't use them. Number one, they are extremely loud. So hopefully not too loud over your speaker there, but very, very loud, especially for its small size. If you could imagine having one that was 100 times this size, right, the noise would be even louder. So far too loud for us to have them on every street corner. And now there's kind of this interesting smell here in my studio as well. So just like we saw in our plasma globe, this electricity actually ionized the gases in the air. It actually took oxygen molecules and ripped them apart, forming plasma. But as they formed back together, they formed a substance called ozone. Ozone is O3, not O2. So O3 or ozone is not so great for your lungs, this small amount, not going to be harmful at all. But if we had Tesla coils on every single street corner, that amount of ozone would be very, very bad for human beings. So bad that we couldn't live with them around us all the time if we could even get over the noise that they create. And so that is it for our Echo Live program today. Join us tomorrow at 2:30 p.m. Eastern for another Echo Live program. We hope to see everyone there. Again, if you like these videos, make sure you share them. If you have any questions, continue to ask us in the chat. Continue to ask us over Facebook. Send us an email. We'd love to talk to you guys. We'd love to bring you more programs. So thank everyone so much, and we'll see you again tomorrow. Have a great day.